Hello, ECE 108, and welcome to a new week of ECE 108. This week, we're going to start off by continuing our discussion of set operations by introducing some useful properties of the operations we introduced last week. This will be followed by introducing two new operations, namely the Cartesian product of two or more sets and the power set. This will be followed by talking about relations and then discussing the concept of functions, which you may have previously seen, but we will be giving a more formal treatment than what you've likely seen in the past. So let's jump right into it. Properties of the union operator. For sets A, B, and C, the following properties hold. The union of A and B is the same thing as the union of B and A. So this property is called commutativity, and it ultimately comes from the commutativity of the OR operator. So next we have associativity. A union parentheses B union C is the same thing as A union B parentheses around that union C. This is an associative type law, and ultimately the associativity of the union operator comes from the associativity of the OR operator. Next, A union the null set is equal to A. So if I take any given set and I add nothing to it, I don't change the set. That's what this states. Next, we have that A union A is equal to A. So this should be fairly intuitive why this would be true. Next up, we have a slightly more complicated property, namely A is a subset of B if and only if A union B is equal to B. So to convince yourself of this, you could draw a Venn diagram to get an idea for why it would be true, but it should be fairly intuitively obvious why this would be true. Finally, we have that if A is a subset of C and if B is a subset of C, then A union B is a subset of C. Now, you can freely use these properties of the union. I would highly suggest that you, at a minimum, intuitively convince yourself why these would be true, or better yet, formally prove them. So speaking of proofs, let's provide a sketch for a proof of the fifth one of these statements, so this guy here. So how would I go about proving this? Well, there's kind of two general techniques that I could use. I could either try to build a chain of equivalence starting with, say, the left-hand side and ending at the right-hand side, such as A is a subset of B if and only if something is true, if and only if if and only if the right-hand side is true. But for this problem, that technique isn't particularly nice. The other way that I could go about it is I could first show that if the left-hand side is true, then the right-hand side has to be true. And then I could show that if the right-hand side is true, then the left-hand side is true. So for the sketch of the proof, that's what I'm going to do. So first, let's examine the forward direction. In the forward direction, I'm first going to assume that A is a subset of B. Now, using this assumption, I need to prove that these two sets are equal. So for showing two sets are equal, I have options. I can either try to build, again, a logical chain of deductions going from the left-hand side to the right-hand side, or I can simply show that they're subsets of each other. So let's show that these are subsets of each other. For this problem, it's just a bit easier to do it that way. So if X is an element of B, then what's true? Well, it trivially follows that X would have to be in an element of A union B. Why? Well, because X is in B. So done that way. For the other direction, I need to start by assuming that X is an element of A union B. So if X is an element of A union B, what does that tell me? Well, either X is an element of A, which then by our assumption is an element of B, or X is in B. So this statement here is what it means for X to be in this union, and in both cases, X is an element of B, therefore A union B is a subset of B. So that's it for the forward direction. Now for the backwards direction. So we start by assuming that A union B is equal to B, and now we ultimately want to conclude that A would be a subset of B. Well, we don't really have much to work with here. So let's try a proof by contradiction. The reason why contradiction is a particularly nice technique here is because this A union B is equal to B doesn't really give me much to work with to try to show that A is a subset of B. So let's just do contradiction and see if it works. So assume for the sake of contradiction that A is not a subset of B. Well, what does this mean? By definition, if A isn't a subset of B, there has to exist some element in A such that that element is not in B, right? That by definition of subset, I need that to be true. Thus, since this element X is in A, it has to be in the union of A and B, right? Just definition of the union. But at the same time, by construction, X is not an element of B. This is a contradiction of our initial statement that A union B was equal to B. Since if A union B is equal to B, then A union B and B have exactly the same elements. Finally, we can conclude that A is a subset of B. For a good exercise, you could do a formal proof of this. All you would need to really do is define A and B before you get into this proof, and then to spell out some of the details here to explicitly state what you're doing in these two cases. Further, a good exercise would be to formally prove the rest of these. You don't have to do that, but you should be able to prove any of these statements if I asked you to do it on, say, a midterm or a final. Next, let's talk about some properties of the intersection. So these properties are similar to the previous properties that we had before, so let's just jump in. So again, we have a commutativity law. So this again is ultimately coming from the commutativity of the AND operator. In addition, we have an associativity rule. We have that A intersect the null set is equal to the null set. We have that A intersect A is equal to A. And we have that A is a subset of B if and only if A intersects B is equal to A. So this is actually extra practice 3, problem 6. So if you want to see a solution of that, you can look there. And finally, we have that if C is a subset of A and C is a subset of B, then C is a subset of the intersection of A and B. So now let's sketch the proof of this last statement, just to give you another example of how to do these types of proofs. So for this case, I only have one direction of the implication to prove. So I can simply start by assuming that the left-hand side is true. So I can say, assume that C is a subset of A and C is a subset of B. So now I ultimately want to show that C is a subset of A union B. So I'm going to do that by showing that any element in C also has to be an A intersect B. So to do this, we first start by saying, and let C and X be given. So now, since X is in C, what do I know about it? Well, explicitly, it follows that X has to be an element of A, because C is a subset of A, and X has to be an element of B, because C is a subset of B. So now that X is an element of both A and B, it follows that X is in the union of A and B by definition. Since X is now in the union of A and B, it follows that C has to be a subset of A intersect B. So now a good exercise would be to prove the rest of these, and do note that you can make this a formal proof by simply stating that let A, B, and C be sets before you make this argument. Okay, now that we've talked about properties of the intersect and union, let's talk about some of the properties that they have when they interact. So for all sets A, B, and C, the following properties hold. The intersection distributes across the union as follows. The union distributes across the intersection as follows. A intersect A union B is always going to be A, and A union A intersect B is always going to be A. So again, these first two laws simply come from the distributive law for the and or operators, and these two absorption laws have an analog in terms of logical connectives, but it's pretty trivial to prove using sets. So let's sketch the proof for the first one of these, just to show you how it's done. So first we can note that X is an element of A intersect B union C. So X is an element of this left-hand side, if and only if X is an element of A and X is an element of B union C. So here I'm just using the definition of the intersection to turn this intersection into a logical connective. Next, I turn this union into a logical connective by applying the definition union and noting that X is in B union C if and only if X is in B or X is in C. So I get that this statement here is true if and only if this statement is true. Now, this statement here is in the form of, say, P and Q or R. So we can now use our distributive law to expand this. So explicitly using the distributive law for logical connectives, I can rewrite this as saying X is in A and X is in B, or X is in A and X is in C. Now this is kind of very similar to this expression here. So now all I have to do is unpack the definitions of union and intersection. So unpacking intersection here and here gives me this, and unpacking the definition of union gives me this expression here, which is precisely what I wanted to show. The proof for the other distributive law is virtually identical to this. You just swap the roles of union and intersection and the and or operators. So a good exercise would be to prove the rest of these. And we're now done talking about unions and intersections for a bit. So now on to something completely different, ordered pairs. In your previous math courses, you considered points in the plane, something like x comma y, or maybe x comma y comma z. Those are examples of ordered pairs. So let's give a formal definition. For some objects A and B, they could be real numbers, they could be integers, they could be cats and lawyers. An ordered pair denoted by AB with these kind of angled brackets is a pair of objects with the property that this ordered pair A1, B1 is equal to another ordered pair A2, B2 if and only if A1 is equal to A2 and B1 is equal to B2. Now, a note on using these angled brackets. In this course, you should use the angled brackets to denote ordered pairs. It's not technically incorrect to use parentheses to denote ordered pairs, but by using the angled brackets, you'll save yourself from some potential confusion in notation later on. Okay, let's look at an example of an ordered pair. In the plane 2 points, where I'm using parentheses because I'm talking about points, x1, y1 and x2, y2 are equal exactly when x1 is equal to x2 and y1 is equal to y2. So points in the plane are examples of ordered pairs. And to be explicit, note that order here matters with points. The point 1, 2 is different than the point 2, 1. Further, note that in this definition of ordered pairs, I said objects. So explicitly, we're not restricted to ordered pairs having real valued components. We could say considered an ordered pair like grandpa, grandson. This would be an ordered pair since a grandson is not a grandpa's grandpa, assuming that the relation grandpa to grandson is by blood. So here I have an explanation for how a grandson can be a grandpa's grandpa. Explicitly, you can be your own grandpa via marriage. It's kind of interesting. You don't have to take a look, but if you want to laugh, there you go. Okay, so now for one more example, prove that for A, B, and R, then AB is equal to BA if and only if A is equal to B. So to prove this, let's go over to Paint and take a look. Okay, so here, if I want to prove this, I need to show that this is true if and only if that is true. So how can we do this? First, I can let A and B be arbitrary real numbers. And next, I can note that A bracket B is equal to B bracket A if and only if their components are equal. So explicitly, I can write this. Now from here, we have that A is equal to B, therefore we're done. So this is a pretty trivial proof, but I just wanted to give another example of dealing with ordered pairs. So now before I continue on to the next topic, let's talk about a computer science application of ordered pairs. So ordered pairs can be used to store information. So for instance, I have a bunch of students in ECE 108, and these students have some grades on their assignments. One way that I can build a primitive database for storing students' grades is to simply build a collection of ordered pairs containing the student and, say, their grade. If I wanted to store more information, I could then change my database so that the second element of my database doesn't just contain their grade, but it could, say, even be a set containing their grade and, say, how often they attended office hours. So this kind of formality of ordered pairs isn't just a mathematical thing, it actually has some practical uses. So now that we've talked about ordered pairs, let's talk about collection of ordered pairs. So the Cartesian product of two sets A and B, denoted by A times B, is going to be the set of all ordered pairs A, B, such that little a comes from the set A and little b comes from the set B. So now let's look at some examples of Cartesian products. So if A is the set of Cat's lawyers and B is the set 1, 2, 3, then the Cartesian product of A and B will be the sets consisting of the ordered pairs cat, 1, cats, 2, cats, 3, and lawyers, 1, lawyers, 2, and lawyers, 3. Further, let's look at some examples that you've probably seen before. Z cross Z, sometimes called Z squared, is simply the set of ordered pairs m, n, such that m and n are integers. Further, the Cartesian product of R and R, sometimes denoted as R squared, is simply the set of all ordered pairs of the form x, y, where x and y are real numbers. So now, why do we want the Cartesian product? Well, this is how we formally define, say, the xy plane, or the xyz plane. So there's a lot of applications of the Cartesian product, and having this definition of the Cartesian product as this collection of ordered pairs has a lot of uses in terms of trying to prove things about objects lying on a Cartesian plane. Okay, let's talk about some properties of the Cartesian product. For all sets A, B, and C, the following hold. Unless A is equal to B, or one of A or B is the empty set, then A cross B is not equal to B cross A. So explicitly, what is this saying? Well, if A is equal to B, then obviously the cross products will be the same. And if A or B is the empty set, then both the left-hand side and the right-hand side will be the empty set. and the empty set's equal to the empty set. Outside of these two cases, if I take the Cartesian product of two different sets, I end up with a different set. Why would this be true? Well, if I go back to the definition, this is an ordered pair, and if A is not equal to B as sets, then I would have different ordered pairs in the Cartesian products. Okay, next we have some distributive rules. A cross the union of B and C is the same thing as A cross B union A cross C. This rule also holds if I put A on the other side. B union C cross A is the same thing as B cross A union C cross A. A similar rule holds for the intersection. A cross B intersect C is simply A cross B intersect A cross C. And again, this rule still holds if I have cross A on the right-hand side. And finally, for set differences, A cross B minus C is the same thing as A cross B minus A cross C. So now let's prove the second one of these. So explicitly, let's prove that this property holds. So before we get into the proof itself, I want you to notice that I'm using the basic methods to show that one set is equal to another set. But in addition to that method, I'm now working with the definition of the cross product. So to prove this expression, I'm going to show that an element is in this set here if and only if that element is in this set. So explicitly, we note that an element x comma y is in this set if and only if y is an element of A and z is an element of B union C. So this is just the definition of the Cartesian product. So next I'm going to unpack this definition of the union just to simplify things out a little bit. So unpacking that definition, I have that. Now this expression is of the form P and Q or R, so let's use the distributive law to spread it out. So the reason why we might want to do that is ultimately I want to rewrite this as x is in A and z is in B, or y is in A and z is in C. And the distributive law lets me write this in a form that looks a little bit more similar to that. So applying the distributive law, I have that y is an element of A and z is an element of B, or y is an element of A and z is an element of C. Now to finish up this proof, all I need to do is unpack these definitions again. So explicitly by using the definition of the Cartesian product, I can rewrite this set here as saying the ordered pair x comma z is an element of A cross B. And here I can rewrite this as saying the ordered pair y comma z is an element of A cross C. So finally, I can change this OR operation to a union operation by using the definition of the union. So here I've shown that an ordered pair is in this set if and only if that ordered pair is also in this set, and therefore I've proven the statement. So a good exercise would be to prove the rest of the properties on slide 7, and do keep in mind that any of these properties here could be fair game to have you prove on a midterm or a final. Okay, now that we've talked about Cartesian products, let's talk about relations. So a relation R on sets A and B is a subset of A cross B. This definition might seem kind of innocent or not very interesting, but relations actually are one of the fundamental building blocks of a lot of the mathematics that you've learned thus far. We will revisit relations in a lot more detail in roughly 2 weeks, but for now let's just examine some examples of relations so you can get an idea of what a relation is. So an example, the set of all points x comma y such that x is a real number and y is equal to x squared is a relation on R cross R. Here I should have used the square brackets, and I will fix that now. So just keep in mind that you should be using these brackets and not parentheses. So next, for any real valued function f, so just think of a function from calculus, for example, the set of ordered pairs x comma f of x for x is a real number is going to be a relation in R cross R. So in particular, you could call this relation the graph of f of x, since it's the collection of all the points that would lie on the graph of f of x if you were to draw it in your standard way. So from here you can start seeing why relations might be useful, because graphs are useful, and graphs, if you define them as the collection of the points in the Cartesian plane, are an example of a relation. Finally, let's consider the relation Q, which is simply going to be the collection of all ordered pairs in m comma n, such that m is an integer and n is a positive integer. Now, this relation is actually the set of all rational numbers. It's written a bit funky. Usually we write rational numbers as m divided by n, but in some sense this set here is the same thing as this set Q. Just change your notation a little bit. To elaborate on this relationship a bit more, we need to cover some abstract algebra, but we're not going to do that in this course. So now, recall that within Q, we have objects that are the same even though they don't look the same. Explicitly, 1/2 is equal to 2/4. So thus, when I talk about Q, I would like to say that these two ordered pairs are equal in the case where M1 is equal to 1, N1 is equal to 2, M2 is equal to 2, and N2 is equal to 4. But by the definition of an ordered pair, they're not going to be equal unless M1 is equal to M2 and N1 is equal to N2, but I would like them to be equal in some special cases. So now how could I possibly quantify these two statements being, quote, equal? Well, if I have two fractions, M1 over N1, and I want that to be equal to M2 over N2, I could simply cross multiply to get rid of the ends, and I could rewrite this expression as M1 times N2 is equal to M2 times N1. So I would like to say that these two ordered pairs are equal if and only if this statement here holds. That is to say, we want two pairs to be, quote, equal even when they have different components. So we can't explicitly do this with ordered pairs, but in 2 weeks when we talk about relations and equivalence relations in particular, we will elaborate on this idea in a bit more detail. So all this stuff here is just giving you motivation for week 6. So now when I'm working with functions or points, I don't always necessarily work with functions in the xy plane, and I don't always work with points in the xy plane. In particular, in Math 119, you're now doing higher dimensional calculus. So I can ask the natural question, do these concepts that I've just introduced still hold in higher dimensions? The answer to that is yes. So higher dimensional Cartesian products. All of the work on the previous slides on ordered pairs, Cartesian products, and relations generalizes to higher dimensions in the way that you would expect. So explicitly, an ordered n tuple is simply going to be an ordered sequence, A1, A2, A3, of n items with the property that two n tuples are equal if and only if their components are equal for all of the components. So mathematically, we can state what I just said in words as the statement here. So to be concrete, in R3, I could talk about x, y, z, and 2 points are equal if and only if they have the same x, y, and z components. So now that we have n tuples, we can generalize the idea of Cartesian products. So if sets A1, A2, all the way up to AN are sets, then the n Cartesian product of these sets, denoted by A1 cross A2 cross cross AN, will simply be the set of all of the n tuples of the form A1, up to AN, where each of the components comes from the respective set. So now, a word of caution here. The Cartesian product is not associative, since A cross B, in parentheses cross C, is not equal to A cross parentheses B cross C, unless one of A, B, or C are empty. So to see why, let's look through an example. So in the case where A, B, and C are all the set that only contains the element 1, what would the cross product on the left-hand side look like? Well, this cross product will simply be the set of all elements of the form 1, 1, and then I'll have these extra brackets around here, 1. So taking the Cartesian products this way gives me an ordered point that's formed by having an ordered point in the first component and then a single number in the second component. On the other hand, if we take the other Cartesian product, this will simply be the collection of this element. So now, this set here is clearly not equal to this set since they're different objects. So this is why the Cartesian product won't be associative unless one of the sets are empty. The set here, I'm writing the Cartesian product of a bunch of sets without using parentheses, and that is a valid operation precisely because I'm defining this notation to define this particular set. So while cross products aren't associative, so technically you would think you can't drop the parentheses, I can define this new object to be this explicit set, so I'm okay. This is just something to watch out for since it could be a potential trick question that I might use somewhere. So now finally, we can talk about n-array relationships between the sets A1 through AN. So this is a generalization of a relationship. So as one would expect, an array relationship is simply going to be a subset of this Cartesian product here. Now these n-array relationships are quite useful in practice. So in terms of previous things you've done with functions, I could use this to find a in-dimensional functions. So instead of talking about x comma f of x, I could talk about x comma y comma f of xy. And also I can use this to build database structures. So using the example I previously introduced about students, I can now talk about, say, a student, their student ID, their email, their mark on each of their assignments, as many things as I want to throw into this in-area relationship. So we have some assigned reading. I want you to read pages 38 through 40 with the focus on the application on pages 39 through 40. And now stop, meme time. So you can now get this meme when you ask your professor if Cartesian products are associative. Well, yes, but actually no. So explicitly yes, because I can make this a well-defined object, but no, because they're not associative in the standard sense. So that's it for this lecture, and I hope you have a good Monday and a good rest of your week.